All right, so rate of change. So let's look at this. What does this mean? It seems like an obvious question, right? We've been dealing with it this whole time. What does this mean?
It's just y prime.
It's y prime. Okay, yeah, that's just another way of telling me, like, it's just another label for it. You're telling me dy dx is the same thing as y prime. Well, that kind of begs the question, what's y prime?
Oh yeah,
And don't tell me it's the derivative, because
yes.
that's again just
Change of
another.
y over the change of x.
What'd you say? Sorry, Colin.
The change of y over the change of x.
Change in y over the change in x. Well, wouldn't that be something like if I had, say, a curve and I picked 2 points and I looked at this ratio, delta y over delta x? Is that what dy dx is? It is the derivative of y with respect to x. So what does that mean to you? So for instance, so we also call it the rate of change, right? A derivative is a rate of change, rate of change of y with respect to x. And I want to focus a little bit more on what Callum said. So but here's a question. So if I told you that, let's say, let's get rid of this. Let's say I told you the slope of the tangent line, this tangent line. Let's say this is x equals a. And I told you that dy dx equals 4 at x equals a. How might you interpret that physically?
Isn't that the instantaneous rate of change at that given point?
Instantaneous rate of change at that given point. Okay, so let's kind of unpack this a little bit further. Let's maybe use a car analogy. Let's say this was, say, 40 miles, let's say it's 40 meters per second. Actually, let's say it's 4 meters per second, right? So let's say, instead of saying x, let's say this was actually with respect to time, right? So let's use t for our time variable. So what if I told you that at this instant t equals a, dy dt, like the speedometer on your car, was 4 meters per second? What that means is if you don't really change your speed, in the next second you will travel 4 meters, right? That's what that means, right? So it's kind of like what Callum said, right? Dy dx gives you an approximation of delta y over delta x, right? It tells you how y changes in response to x. So that's what we're going to be kind of focusing on a lot today. So let's see. So dy dx, sorry, well, it's actually the other way around. Right, delta y over delta x is an approximation of dy dx, right? If x changes by delta x, then y changes by what? Delta y over delta x times delta x, right? In other words, the derivative at that point times delta x. So the derivative gives you kind of a measurement of how much the y variable changes in response to the x variable. If you change x by a little amount, this is what y will change by. So if dy dx, what would it mean to say that dy dx, say, equals -4 at a point? That means if you change x by a little bit, y will decrease by about 4 times that amount, right? So if I increase x by 1, y will probably change but decrease by about 4. That's what that means. Now, obviously, we know this is not exact because in general, curves have a variable slope, right? So between these 2 points, even if I tell you the slope of this tangent line is 4, obviously, if I increase x by 1, in this particular case, y has not increased quite by 4, right? It's a little bit less, but remember, it was just an approximation, the dy dx, or the delta y over delta x. Okay, so we're going to do some, quote, real world applications of this, right? This is actually a pretty important section because, one of the few things that we really want you to take from calculus is probably how to interpret rates of change, right? Okay, so